When people say AI agent, they often picture a chatbot with one smarter prompt. In production, the real thing looks more like a distributed software system wrapped around a model. A serious agent has to accept work, hold state, call tools, read memory, enforce permissions, and survive failure. If any one of those pieces is weak, the model can sound impressive while the platform still makes bad decisions. That is why the core architecture matters. Queuing, storage, policy, caching, tracing, and deployment design often determine whether the agent is useful, expensive, or dangerous. In this video, I will build the full platform in layers: model layer, orchestration, tool registry, memory, vector search, relational storage, queue, cache, secrets, policy, observability, CI/CD, and cloud deployment. We will use one running example all the way through. Imagine an agent helping a cloud team investigate a failed Kubernetes deployment and prepare the next safe action. That example is useful because it forces the agent to read current state, inspect logs, retrieve past context, respect permissions, and stop before unsafe changes. By the end, you should be able to sketch the core platform, explain what each layer does, and separate the model from the rest of the agent system. I also want one rule to stick in your head. A serious agent is not just an AI feature. It is an engineering platform with control loops and guardrails. Start with the simplest definition. A production agent platform is a system that lets a model reason over context, choose actions, use tools, store state, and continue toward a goal across multiple steps. The model layer sits at the center, but it is only one layer. The model interprets language, ranks options, and can propose tool calls, but it is not your scheduler, source of truth, or security boundary. Around the model sits the orchestration layer. This is the run manager or state machine that decides what step comes next, what context to include, when to retry, and when to stop. Below that sit the memory and data layers. A memory store keeps working state, a vector database helps retrieve semantically related knowledge, and a relational database holds durable facts like runs, users, approvals, and audit records. Now let's build the platform. At the edge, requests arrive through an API, chat surface, webhook, or scheduled trigger, and they usually enter a queue before a worker begins the run. Next comes orchestration, tool routing, and policy. The orchestrator chooses the next step, the tool registry describes available actions, and the policy engine decides what the agent is allowed to do. Beside that, the platform needs stateful services. The memory store tracks the live run, the vector database helps with retrieval, the relational database stores durable truth, and the cache avoids repeating expensive lookups. Under and around the runtime, you also need a secrets manager and observability stack. Secrets keep credentials out of prompts, while logs, traces, and metrics make the agent debuggable in production. Here is the runtime flow. A deployment incident request arrives, gets authenticated, receives a run ID, lands in the queue, and is picked up by an available worker. The worker asks the orchestrator to build context. That means reading recent run memory, checking cached facts, querying the vector database for relevant knowledge, and pulling durable records from the relational database. Then the model reasons over that packaged context and proposes the next action. If it wants a tool, the tool registry resolves the contract. The secrets manager provides credentials, and the policy engine checks whether the call is allowed. After the tool returns, the orchestrator observes the result, writes new state back to memory and the database, emits traces and metrics, and decides whether to continue, ask a human, or stop. Now the warning. If there is no policy engine, the model can request tools it should never touch, or jump from diagnosis into execution without approval. If memory is sloppy or retrieval is weak, the agent can work from stale tickets, wrong environment details, or semantically similar but incorrect documents. That looks intelligent right up until it breaks something. If there is no queue, cache, or retry design, the platform becomes noisy and expensive. Duplicate jobs pile up, timeouts multiply, and the model keeps redoing the same work. And if observability, audit trails, and secret isolation are missing, you cannot explain what happened, prove who approved what, or rotate credentials safely after an incident. The better pattern is governed execution. The agent can analyze, retrieve, and prepare options, but high-risk steps pass through a policy engine, approval gates, and deterministic apply rules. To ship this safely, you also need CI/CD for the platform itself. Prompt templates, tool schemas, policies, retrieval settings, and integration tests should move through version, control, review, validation, and staged rollout. For cloud deployment, think in services. Put the API and workers on managed compute or Kubernetes, keep the queue and cache managed, place databases in private networks, and use a secrets manager plus least privilege identity everywhere. Finally, close the loop with observability and resilience. Collect traces per run, logs per tool call, metrics for cost and latency, dead letter, failed jobs, autoscale workers, and back up the durable stores. So the core architecture is not model first, it is system first. The model sits inside an orchestrated platform of tools, data stores, policy, secrets, queues, cache, observability, and cloud operations. The simplest operating rule is this: let AI reason, but let the platform verify. That one rule improves safety, debuggability, and trust immediately. At Trustscrin, we are building tools around this problem because moving from architecture ideas to governed execution is where real engineering value shows up. If you want more practical videos on AI engineering, Terraform, Kubernetes, and cloud delivery systems, subscribe and I will keep breaking these production patterns down step by step.